Hello, welcome and thank you for taking the time to watch my final year project presentation. My name is Ahmad Fauzi and I will be sharing with you the study of the impact to the head. For introduction, I present the study titled Finite Element Analysis of Impact for Helmeted and Non-Helmeted Head. In a world where safety is paramount, the research focuses on critical aspects of head protection and effectiveness of helmet in mitigating impact forces during accidents and collision. Head injury, particularly traumatic brain injuries, have far-reaching consequences affecting not only physical well-being but also cognitive function. Such injuries can lead to cognitive difficulties, language difficulties, and affecting the individual quality of life. Objective of this study is to investigate the head and skull impact. This objective is to thoroughly investigate the impact on the head and the skull when involving in a frontal collision. Secondly, is to analyze and understand the specific effects of this collision when the cyclist or when the accident is traveling at varying speeds. Next is the methodology of the study. We have the literature review where we conduct when we conduct a review of the relevant scientific literature and research papers. We have data collections where we will collect inside data related to the head, to the skull, and the biomechanical properties of helmets and other protective gear. We have finite element model development where we develop models of head and helmets. And we also do impact simulation. And we evaluate the helmet effectiveness, comparing them between different material thickness, and then we have data analysis, and finally we do recommendation conclusion followed by a report. The literature review which has been conducted has revealed several findings. To begin with, helmets have demonstrated remarkable success in specific application, particularly in reducing moderate to severe head injuries. Helmets have the potential to modify two primary head injuries, namely concussion and severe head injuries. Depending on the sport, up to 50% of injuries to the body region are head injuries, and concussion account for up to 15% of all sport injury. Currently, helmet design feature energy absorbing liners which are optimized to reduce linear acceleration of the head and mitigate related injuries such as skull fractures. Now, the human brain is sensitive to rotational motion. A pure radial impact, which is although rare, can cause linear acceleration of the head, primarily resulting in skull fractures. A diagonal or oblique impact, here we have it, tangential impact, are more commonly known to induce both linear and rotational head acceleration. As the force impact around the head center of gravity, which will cause rotational acceleration to the head, and in this case will cause head injuries such as concussion and traumatic brain injuries. The brain tissue can be likened to a fluid, and its primary mode of deformation is shear. This observation highlights the importance of considering rotational forces in head impacts as they can significantly affect brain tissue. Rotational acceleration might serve as a more accurate indication of traumatic brain injury than linear acceleration. These findings emphasize the relevance of rotational forces in assessing head injury. Severe head injuries such as hemorrhage are more likely to be caused by rotational head motion. Understanding this link is crucial for identifying injury mechanism and designing an effective protective head measure. Traumatic brain injury. Traumatic brain injury occurs when a moving head collides instantaneously with stationary rigid object. Understanding this scenario is crucial for analyzing head impacts. Also, traumatic brain injury are associated with two main destructive forces, contact and inertia. Contact, which involve direct collision, and inertia, which accounts for impact resulting from sudden change in motion. Head injuries account for a substantial percentage of fatalities in bicycle accidents, between 69 to 93%. Bicycle safety helmets have demonstrated their effectiveness in various studies. Their role in preventing head injuries is a vital component in promoting overall bicycle safety. Helmets have proven to be highly successful in preventing a range of head injuries, particularly moderate to severe head injuries. Due to variation in human tolerance to impacts and impact profile, helmet must be specifically designed and developed for different age groups, including children, adults, and older athletes. This variation is essential to create helmets that provide optimal protection and ensure the safety of individuals across different age ranges. Finite element analysis. This is a powerful tool used to study the impact or response of the human head and brain and the helmets. Firstly, we create a realistic model, which involves creating a model of human skull and helmet. Currently, the magnetic resonance imaging, or MRI, is a primary method used to construct detailed 3D models of the human heads. To enhance the model accuracy, material properties are assigned to different structures of the head, such as the brain, skull, and helmet materials. The brain material property is assumed to be isotropic and linear viscoelastic, following which the second finite element model is developed is the protective helmet, consisting of the top shell and foam. HIC, which is a head injury criterion, is a function dependent on time and head acceleration. If the HIC values goes up to 1,250, this is non-dangerous to human life. HIC value up to 1,250 are non-dangerous to human life, while more than 1,500 are fatal. Between these two values, they are injuries of moderate severity. The severity of damage to the skull and brain was found to be dependent on three key factors. Firstly, the orientation of the head at the moment of impact. Number two, the velocity of impact. And thirdly, the mechanical properties of the barrier involved in the collision. The most dangerous impact were identified to occur at the parietal and temporal area of the skull. These specific regions are particularly vulnerable due to having the lowest bone thickness in the skull structure. Increasing the thickness of the foam layer in the helmet resulted in the reduction in the magnitude of the acceleration. This reduction in acceleration indicates that thicker foam layer contributes to mitigating the intensity of the impact forces. On the other hand, the results show that increasing the thickness of the outer shell of the helmet has a negative impact on the helmet damping properties. A thicker outer shell is associated with decreased damping, potentially limiting its ability to absorb and dissipate impact forces effectively. So in summary, helmet play an important role in head injury. A key finding in our research is the importance of tailoring helmet to different age group as human tolerance and to impact profile varies across children, adult, and elderly. Designing helmets specifically for each group can enhance overall head safety. Moreover, our investigation revealed that the extent of skull and brain damage during impact is influenced by various factors, including the head's orientation, impact velocity, and mechanical property of the barrier. Understanding this influencing factor is essential in devising effective safety measures and designing helmets that can better attenuate impact forces. For future work, we'll be creating a working model of a skull and helmet. We will test and compare helmets of different material to best suit and protect the head, assess the effectiveness of various helmet material in reducing the risk of head injuries, and the evaluation will focus on analyzing the capability of different helmet material to attenuate impact forces and minimal potential for head trauma. I thank you very much, and please leave any questions in the comment section. Thank you.